Hi, welcome to another edition of Design Spark Ask the Expert. Today we're going to be talking about thermal management with Wurth, and I have Sebastian Marisol from Wurth. Hi, Sebastian. Do you want to say hello to Design Spark?
Yeah, absolutely, Greg. Thanks for having me here. As Greg mentioned, I'm Sebastian. I've been a product manager for nearly 4 years now in Wurth Elektronik, and my main area of expertise is thermal interface materials.
Okay, so Sebastian, thermal management, why is it so important to have good thermal management of electronic devices?
Yeah, well, I've always liked the wording, right? Thermal management, and that's really important, the management bit, because that's really what it's all about. It's about taking heat energy from where you don't want it, like components and so on, and transferring somewhere else that it doesn't bother you. Like, for example, the ambient is the most um, commonly used solution. And why is it important? Well, it's really important because from two very related topics. One of them is the component level reliability. If we have a look at, I don't know, any active component manufacturer like transistors, ICs, or whatever, we always see that, junction temperature that should not be avoided in order to, expect the full lifetime of the component and so on. So thermal management is about that. It's about helping active as well as passive components, of course, work within the expected range so that we get, manufacturers, they are clever, they know, they're good designers, they know how their components behave on the long term, on the short term, and different operating temperatures, and that's why they always give us those temperatures to respect.
Mm-hmm.
Yeah, and also we've talked about the reliability of the component, but of course that extends to the reliability of the device or the design that you're working on. If you don't have any reliable components, then your final design is going to be flawed, and that's what we don't want. We as designers, we always want our devices to work for a very long time, and that's why we have this amazing field, which is thermal management, to keep that in check and make sure that all our designs are optimal and they work for as long as we have designed them to work.
Okay, so yeah, it's absolutely an important part of the design. I'll probably come back to you on that. But I'm sure most of us, in some form of cooling, we remember, back in the days of the old desktop computers, the cooling fan kicking in if we were doing a lot of processing, for example. But fan obviously is one method of cooling. What are the other methods of cooling in the electronics environment?
Well, before we get into that, we have to really define or have a look at how thermal energy behaves within any kind of system, and it behaves by moving in three different ways. One is the first one is the obvious one, which is conduction. So if you have a metal rod and you put a metal source on one side, you're going to feel the heat on the other. You also have convection, which is what happens when that thermal energy is transferred to the ambient, and especially an ambient within an atmosphere. And then you have, of course, radiation, which is something that appears mainly, in space or vacuum applications, but nevertheless, it's always present. Because if you remember from any kind of barbecue, or if you've been out in the wild and made a fireplace or somewhere, especially during winter, when you are in front of the heat source, you feel the heat. But if someone walks by or blocks your visual of the heat source, you don't feel that much heat again. And that's because even though we're inside the atmosphere, it's still, of course, radiating energy. And even though we have those three ways of transferring or conducting heat, they're all present at the same time, depending on the ambient. If we are inside the atmosphere, outside the atmosphere, inside our devices, and so on, one of them is more prominent than the other, but of course they all work at the same time because we have our heat sources, which are our components, and then we are transferring the thermal interface materials to a heat sink. And that heat sink is then transferring all that thermal energy to the ambient via convection on one side, and then also a little bit of radiation. That's why sometimes we see the heat sinks anodized in black, because that gives a little bit of a boost because they are able to radiate more energy and perform a little bit better. that's basically how we do it. But yeah, now that we've defined that, we also have, well, there are like two main, very broadly speaking, of dividing cooling. You've got passive and active cooling. Passive is when your system doesn't use any kind of external application or external device to achieve the cooling. Normally, it's where we have the heat source, the component transferring the heat to a fan, and that fan passively is transferring the thermal energy over to the ambient rather than
Yeah.
being pushed by a fan or whatever. So yeah, and it comes with some advantages and disadvantages. The advantage is that it's cheaper in cost because you don't have any kind of external need for any kind of device or anything. But also, it's very dependent on you doing a really good thermal design of making sure that the you're offering thermal energy the path of least thermal resistance from the source down to the ambient.
Okay, so
It's more, yeah. Sorry,
that's the key characteristic is making sure we get out to the ambient as quick as possible. Is that right?
Rather than as quick, as least thermally resistive as possible, because heat energy behaves a lot or we like to make an analog. Some people call it not a correct analog with electricity, because thermal energy always flows from the heat source to the reference, which is normally the ambient. So if we remember from electronics, we have current that flows from the source to the sink. Or to the reference rather. And every time we have anything in the middle, any resistance in the middle, we're going to have a voltage drop. Thermal energy is exactly the same. Every time we have a different material in the middle, that's going to be bringing a thermal resistance into the system. And that thermal resistance is going to be bringing a temperature above ambient rise, I think it's called, yeah. So it's always about providing the path of least resistance so that we don't have those rise above temperatures within our system. That's why we always look for higher performance thermal interface materials and so on. So that's a little bit the difference. And then, of course, when we talk about active cooling, that's where external things come into play. We can have a fan, we can have a pump working by pumping liquid to a radiator and so on. And of course, these kind of systems are able to move a lot of thermal energy from the source to the ambient or to wherever you're releasing it. But of course, it comes to with a higher cost because you have those additional hardware that you're not having with the passive cooling. So also brings a little bit more complexity into the system. That's why, if you let me, I can share this little graph I have over here, which really shows thermal efficiency versus complexity. We have different ways of cooling. Natural convection and radiation is the bottom one. That's the one that is passive cooling, and then all the other ones are a little bit more active because you've got forced convection, you've got fluid phase changer, and thermoionic cooling, which is something rather new, and then of course liquid cooling. So as we can see, as we jump from passive to active, we see a really good increase of how much power we can dissipate from the surface of our cooling system. Of course, the more efficiency we have, the more complexity it brings to the system, because it's of course not the same from the probability of failure of having just a passive heatsink just passing thermal energy down to the ambient, rather than if we go to liquid cooling where we have, a pump that is pumping a liquid. That liquid sometimes thermally degrades over time, needs replacing, the pump can fail, and so on. So that's why all of them have their perks, but all of them also have their issues. And this is always going to be a recursive thing when we talk about thermal management. It's always a compromise between different things: efficiency, costs, and of course end user requirements, because it's very broad. Thermal management is something that is applied to many different disciplines within electronics, power electronics, data acquisition, electric vehicles rather. And so they all each have their own special requirements, and some things sometimes apply to some of them, and something sometimes doesn't apply to all of them. So it's a little bit, yeah, tricky, and always about that, a compromise.
Okay, that's quite clear, that slide. It just really breaks down the different levels there. So yeah, thanks for sharing that with us. That's really good. So in terms of when we're looking at the design process, so obviously things like EMC and RF need to be considered in the design process. But when should engineers look to decide on the cooling method that's most effective? And like I think what you were mentioning, it could be a measure of different cooling methods needed to be considered. Is that right?
Yeah, exactly. And that's a great question because, as I mentioned, thermal management is always a compromise between performance, cost, and user requirements, or rather application requirements. And thermal management is something that it doesn't fall into anyone's plate, really. When we think about electronic design, we know that PCB designers are really good at layouts. Electronic designers, they're good at supplying ICs or whatever other components, what they need and so on. But thermal management, it happens a little bit also with EMC. It doesn't fall into anyone's plate, and it's really something to keep an eye out for, because the way electronics are designed nowadays, you have, as I mentioned, an electronic designer. He's working on the functionality of the device. He's making sure that he's getting or creating the power resources needed by the components, keeping in mind, small form factor, energy efficiency, those kind of things. And then once they have like this schematic or this design, they then forward it to the PCB designer, which is the one that lays everything on the board, taking into account all the previous things, but also worrying about, signal integrity, noise, EMI, and so on. And then when we have that PCB, is then passed on to the mechanical engineer, who then works to get that PCB into a physical enclosure. And this is the first time that the whole system has come together. It's mostly tested, and that's where the thermal issues come up, or the first time that they are actually being considered. And it's a really bad timing for this, because you're nearly at the end of the project. Here you have mechanical spatial constraints. You also have time to market pressures. You have limited remaining budget, and so on. And these kind of things are always playing against you.
Yes.
Especially at such a bad time that then another problem, which is thermal management, comes up. So it's something to really keep an eye out for. And the most effective method to consider thermal management in the design process is to keep it in mind right from the start, to really, come together and decide, okay, what amount of energy will I be needing to dissipate into the ambient? What is active cooling going to be an option in my application? Is it not? What amount of power am I going to try and dissipate? What also another thing to consider that sometimes we tend to forget is, where is my design going to be operating in? Because of course it's not always having, a piece of networking equipment in the Australian outback rather than working in Siberia. It's very different conditions, and you have to consider many different things in order to have that optimal thermal performance for the device. Because let's not forget, what we are doing is, making sure that our device in the end is reliable. And that's why thermal management needs to be understood as a system, because you've got many inputs and one output, and everything plays a role. And you really have to think of it as a whole system. And normally, the first approach is always to have the analytical approach. I know which components I'm using. I know what power I need to dissipate. I know what amount of energy I can transfer to the ambient. If I have these thermal resistances right between, I can more or less calculate what my junction temperature is going to be. But nowadays we have like really powerful tools, which are the simulators from ANSYS, from Cadence, and whatnot. And they really do help the designer to estimate with more precision what that system is going to be. Because the analytical approach, the one we used to have in the beginning, with doing our equations and so on. It's very much focused on static, how do you call it, like static environments.
Yeah.
But then, of course, electronics lives in a time constrained world. So in reality, everything is transient. You have peaks, you have planes, and so on. And then, of course, how everything interacts with each other. And then that's why simulators come really into hand, because the analytical way you can get to one point, but if you want to take it to the next step to really have a global system-wide vision, that's where simulators really do help you. And you don't have to simulate like a whole PCB like we're used to seeing in these fancy shows and show and tells where you have this computer motherboard, everything simulated and so on. No, you can even just stick with small blocks which just generate temperature, more or less. This is what the housing look like. This is the cooling I'm going to be using. That's just enough to get a really good estimate of how well it's going to perform the system. So something really definitely to keep an eye out for.
Great. There's some great tips in there. Obviously, really needs to be factored in at the beginning of the design. You need to give due consideration to your thermal management, similar to how you would if you were testing for EMC, because as you mentioned, if you get to the end of the product design and you have to go back retrospectively, that adds a hell of a lot of cost to the whole project, for example.
Indeed.
But then again, the use of simulation, for example, giving it a real life environmental feel around that, and then how influence from external factors can influence the life of the product and how to bring in good thermal management. That brings me on to a current trend that we're seeing. So in terms of if we're looking at electronics, there's obviously a big movement to miniaturization to get more performance out of components and devices, but to have those contained within a smaller area. So the impact, I would imagine, on thermal management is great. Is there any advice that you would have to maybe overcome some of those hurdles?
Yeah, I mean, the most important one is, as I mentioned, keeping thermal management as a system in mind, having it in the designing process, and also it's also like with EMC, really keeping in mind your components and how they are laid out on your board really does have a huge impact. Of course, it goes against some of the even rules of thumbs in giving also in EMC, where if you have things sometimes closer together, you're not going to have issues. Here, it's exactly the opposite. It's about keeping heat distributed more or less, try and have it evenly distributed throughout a PCB. And the only way you can do it, of course, is by component placing.
In terms of thermal management, do you see effective thermal management being like one of the main drivers for sustainability within the electronics industry?
Oh yeah, especially now that we are getting into a very interesting place with these new technologies, 5Gs, electric vehicles, or e-mobility, and so on. We're really getting into a place where thermal management is starting to be a topic that is bringing by itself present to electronic designers, because before we used to have much larger components and we had more room for them. And the analogy I always like to make is that if we go back in time and remember the first computers, they were whole rooms, like just full of PCBs and full of cables, and the thermal management there was just the air that was inside the room. Then one day they said, oh, if we add air conditioning to the room, yep, go for it. But then things started getting faster, things started getting smaller, power densities were much bigger. You had many more power hungry components closer together. So it really did start to become an issue, and that's where all the interesting things started to happen. First of all, we had the heat sinks. Then we started to think, oh, could we really interface better with heat sinks with these components? And that's where thermal greases and paste came into play. And then we started saying, hey, what if we've made the computers small enough, what if we made them small enough that we could actually carry them in a briefcase? And then many more problems started showing up, and then other solutions came by, because after all, that's what us engineers we like to do, come up with solutions to problem. And so new materials came into play. We have now copper heat pipes being used within computers that they are able to transfer heat energy from one place to another where it's more comfortable to put a fan and a heat sink. And then even newer materials such as graphite heat spreaders came into play where they were able to have these really dense, power dense areas with lots of small components and try to spread the energy as a bigger surface as you could, so that you could transfer more to the ambient. And this is something that I always like to mention with mobile phones. We've all been, having some downtime looking at videos on our mobile phones, and we started feeling them get hot on the backside.
Absolutely, yeah.
Yeah, exactly. We've all been there. So,
or we leave them in the sun and they overheat. Yeah.
exactly. Yeah, and the reason because of that is that because you have many small components very close together, and they don't have enough space to actually dissipate the heat, and that's why phones get hot, and you can feel more or less an area, but not a particular point, and that's because they are all using heat spreading materials to actually help to transfer that thermal energy for as much area and for as much the ambient as possible.
Okay.
So yeah.
That's a nice little lead into to my final question, Sebastian. I just want to know a little bit more about Wurth and obviously the portfolio that you guys have and how you're helping to deliver thermal management solutions, maybe the materials. So basically, for engineers, what is it that they can look at from your ranges?
Yeah, absolutely. Well, as I mentioned right at the beginning, we're focusing on thermal interface materials because thermal, it's a system. You have your heat generator, you have your cooler or transfers to the ambient, but of course, what happens in the middle is also really important, and that's where we have focused our portfolio right now. We've divided it into. If I can quickly share my screen, we've divided it into three areas. Mainly gap filling solutions. This is what everyone is used to for the last, I don't know, 50 or so years of seeing, these silicon elastomer pads like the TGF, these insulator pads that we've also pretty much seen in all transistor applications. And then with the new things such as LEDs came other solutions like the thermal transfer tape, which is able to not only provide a thermal interface between the hot component and the cooling assembly, but also to mechanically fix it so that you don't need any kind of additional screws or anything. And then we have the phase changing materials. These ones, they're also really interesting. They've been around for a couple of years. And the interesting thing is that we've always talked about, the bringing into a system the least thermal resistance. And the way we do it is by having as thin as possible and as wet as possible. Because when we think of two surfaces coming together, we see them as completely flat, like a component top and heatsink. But if we looked at them under a microscope, we would see like that those surfaces are not actually as flat as we thought. They're pretty rough.
Okay.
So with this material, what it brings to the table is that it's solid at room temperature because it's based on wax, like candle wax, basically. So it's really easy to handle. It's hassle-free. You don't have to have any kind of special dispensing equipment on your production line or your assembly line rather, that can, lead to leaks and so on. So it's solid. And then once the component, the hot component reaches a temperature of around 50 or 60 degrees, it changes phase into a liquid or flow-like state, better said, where it really does fill all the microscopic gaps and really provides a really good thermal interface between the hot component and the heatsink by providing the path of least thermal resistance. So it's something really, really, really interesting, especially for high-speed applications like FPGAs and so on. And it's also hassle-free, which is always nice to have. So those are the four main gap fillers, and the reason we have so many of them because they more or less each fulfill different customer requirement. Gap fillers are elastomer gap fillers like GF are the backbone of the thermal management industry. They are very versatile. They come in very thermal in a very wide range of thermal performances, and they also have many different thickness layers so that you can fill smaller or big gaps. And yeah, and that's a little bit how each of them plays differently. Now, as I mentioned also before, we also have spreading solutions in the market. In Wurth Elektronik, we have the graphite sheets, the TGS, which is an acrylic coated graphite because, of course, graphite is electrically conductive and you always want to maintain isolation. And yeah, and basically it's that. It really does help to spread the heat throughout the horizontal plane. If we compare it to, for example, all the traditional gap filling solutions, which are more or less in the between the 1 to 6 watt per meter Kelvin. For the graphite, we're talking about a performance in the horizontal axis of around 1,800 watts per meter Kelvin, depending on the thickness of the material. So it's very different. Of course, it doesn't mean that you're going to have this thermal conductivity throughout, like a very long strip where you are going to apply heat on one end and then on the other you're going to feel the exact heat. But it really does help, especially in those power dense applications like we mentioned, mobile phones or any kind of handheld devices where things are really close together to actually spread the heat over to metal housings or enclosures. And then we have the hybrid solutions, which is a little bit like that. It's a hybrid. It's taking a horizontal heat spreader and wrapping it around a foam core.
Yeah.
So what we're doing basically is we're taking and making a horizontal heat spreader. We're making it into a vertical one. And it really does bring some advantages to the table because one of the limiting factors of the gap filling solutions is, of course, the thicknesses, but also you have to really ensure that the surfaces are completely coplanar. Because then if you have any kind of vibrations or something, then you're going to have the pads probably be pushed out, or rather if they are more compressed on one side than the other, it can lead to some unwanted mechanical events.
Yeah.
So the interesting bit about the graphite foam gaskets is that, again, coming back to what we mentioned earlier, when the final device is assembled and you see, oh, my PCB, the component I want to cool doesn't have a completely flat surface. It has like a weird angle or a railing or something, and I cannot interface it with that. The good thing about the graphite foam gaskets is that the foam, you can actually have it in different profiles. So you can do a profile that really fits your gap, even though it fits, more compressed on one side than the other. And so it really brings other advantages that the traditional ones doesn't bring. Besides, of course, the higher thermal conductivity, but of course, thermal performance of these materials are always very application dependent. And this is something that I always like to bring up, which is that each application is more or less their own. There is no universal solution, and this is why thermal management it's a system, because you have to test it, you have to prototype it, and then you have to evaluate it to rather ensure that you really do have the most optimal solution. And of course, higher thermal conductivity is not always something, it's not comparable. Like having a really high thermal conductivity does not imply that your system is going to be cooling more, especially in interface materials, because there are many other effects that come into place. Like, okay, what do the contact surfaces resistance have? Of course, a material that's wet, like the PCM and the TGF, which have like a silicone oil on the surfaces, they really do help out to match those surfaces and reduce the thermal resistance. So maybe even if the TGF has, for example, a worse thermal performance in comparison, let's say, to the TGFG, which has 400 watts per meter Kelvin, we might see that in our particular application, actually the TGF is behaving better. Higher thermal conductivity does not always mean better thermal performance, because thermal conductivity is what we call bulk measurement. So that's like the ability or the capability of the material to let the flow of heat go through it. But rather, what really does have an impact on the performance of the systems is, as I mentioned before, the thermal resistance. This, of course, does change. The more you compress a material, the thinner it is, the least thermal resistance it brings. That's why maybe we see some applications where the TGF, even though it has a worse in paper thermal performance than the DGFG, it performs better because there are other factors that come into play within thermal management, like the thermal resistance, the thermal contact resistance, and so on. So it's always a compromise between many different things.
Sebastian, this has been a really great conversation on thermal management. I think, you know, in the short space of time that we've had, you've covered in depth quite a lot of the knowledge, you know, that you have and you're sharing with our viewers. So I really do thank you for your time today on Design Spark, and I hope, you know, we can have you on Design Spark again sometime soon.
Yeah, absolutely. Thank you for having me here.